We all do that.
You will.
So my name is Lezcano. I'm working in Linaro, the power management working group. So this is related to power and improving also performances. So the presentation is about the cooling device. Today we have in the mobile market, we have a lot of innovation. And in this innovation, we have features like augmented reality or virtual reality, high resolution movies, and all these applications are CPU intensive. And of course, because they are CPU intensive, we have more performances, so more power use, and higher temperature. So in order to explain that the problem we are facing with the thermal, we have to explain three concepts about the thermal. So the first one is the dynamic consumption, the second one static leakage and thermal runaway. For the dynamic consumption is quite simple. It's the power drain, the energy drained by the circuitry when it's used, and it relies on an equation, the capacitance, utilization, voltage, and frequency. So these terms, capacitance and utilization, are grouped together because these values are hard to get from sub vendors. So in the kernel, we have the dynamic power coefficient in the DT, giving the resulting of this factor, capacitance and utilization. So we can compute from the kernel, we can compute the power at a specific OPP by using the equation for C dynamic times frequency and voltage. So the important thing is to understand that we have the voltage square. So each time we change the OPP, the energy consumed is increasing in a logarithm way. So this figure, you can find that on internet everywhere, gives you an indication. So, for example, for this this figure, we have the frequency is 1 gigahertz, and if we look at 2 gigahertz, the power consumed at 2 gigahertz, it's 4 times what we consume at 1 gigahertz. For the static leakage is the normal energy drained by the circuitry, not being used, but it's constant. It depends on temperature, so when the temperature increases, static leakage increases also. And the only way to drop the static leakage is to power down the component. And then we have a third phenomenon, which is a thermal runaway. So in this situation, we have the component is heating more and more and more. And even if we stop using it, for example, reducing the frequency to 0, because of the silicon, we have the current is still growing inside and it's still dissipating more power, heating more, and the temperature is still increasing. So it's a runaway. It's a dangerous situation where we can have the silicon dying there. So the only way to prevent that is to pour down the component. Otherwise, we might burn the component. So in the kernel, we have a way to prevent that, we have the mitigation, and usually we know the mitigation on desktop computer that is done with active cooling device like a fan. But obviously, we cannot have a fan on a mobile, so we need to have a passive cooling device, and that's the purpose of the CPU cooling device. So the idea with the CPU cooling device is when the temperature is increasing, and we reach a specific threshold we define in the device tree, we reduce the frequency. And then as soon as the temperature is decreasing, dropping, then we increase the frequency again. So for that, we have the sampling there. The sampling is getting the temperature based on a polling. You find the polling in the DT. The sensor is on the sock, is giving the temperature back. Then that's transmitted to the governor. We have different kind of governor in the kernel. We have the power allocator governor, which is based on power computation and using a PID loop. We have a statewise to increase and decrease the state of the cooling device. Bang bang, changing the state very quickly. And then we have one cooling device for CPU cooling device for in the mobile, where we drop the performances. So here, these three figures we show that. Oh, I think it's not frequency, it's temperature. So with a high load, we see that the temperature in this board is 75 degrees, and we see that temperature is around 70 degrees until we reach a point where the temperature decreases, and that's because here the cooling device is changing the OPP. So here we have the OPP, we have two clusters, and this OPP change will decrease the temperature. So we see that we are at the beginning we are jumping from 2.4 gigahertz to the OPP just below 2.2, and then we go just 2.4 to 2 gigahertz, and then we have big changes from the highest OPP to the lowest OPP. And that's the way the CPU cooling device is mitigating the temperature on the circuit.
What was the governor over there?
Stepwise, this one. So yeah, we have now with the recent hardware, we can have very high frequencies, and of course we have to dissipate more power. And also, what is new is we have the transitions. The transition between in the temperature is very fast. So for example, for some boards, we have I think it's 40 degrees in 10 milliseconds. So it's very fast. So of course, if we want to mitigate this kind of board, we also have to poll very quickly in order to sample the temperature, because the changes are very fast, and that's also CPU intensive. So we are adding more heat. So we consume power to save power. And of course, we are very quickly reaching the heat capacity of the sock by with this kind of hardware. So what we would like to do is to drop performances like cpufreq, but also drop static leakage in order to let the circuitry cool down, and be able to reduce also this heat which was accumulated on the sock. So the idea is, instead of reducing the frequency like the CPU cooling device is doing today, we want to force the CPU to do nothing an amount of time. There is a similar mechanism called interprogram doing that today, but it's a bit different. So the idea is to synchronize the CPU, the idle at the same time, in order to group that, to have this, the CPU be able to give the opportunity to the CPU go cluster go down. Of course, they have to be all the cores belonging to the same cluster must go idle at the same time. Otherwise, they can do a cluster go down. And by letting the CPU go into the cluster fall down, we can, of course, the components around can be can also be brought down, and so we we have a way to let them fall down more, faster and more efficiently. So the idea is to inject cycles, fixed idle duration, and reduce the period of these idle cycles. So when the temperature increase, we have more idle cycles, and when it decrease, less idle cycles. When there is no mitigation, there is no idle injection, and when we have full mitigation, 100%, we are almost the stock is pulled down. So we have an idle task with a fixed idle duration. So this idle duration doesn't change, and we have the idle injection period in both. So when we begin the mitigation, we reduce the period until we have a situation where we are mostly idle. But that should not happen. So for that, we need to compute the duration of the period. And in order to compute the duration of the period, we have some math. And this math is an average. We have a power here, and the average of the power is we are running of the power on this OPP level during an amount of time, and we are idle an amount of time at this power level, and then we have the average here. So we are interested in having this value. What is the period here? So we know the time will be idle. For example, we say it's 10 milliseconds. And from there, we can change the equation to have time to idle of time running or time running with all the information in there. So the power of the different OPP, we can compute that directly from the DT because we have all the information. The time, the idle duration is so we know this information because we decide how long we will be idle. So, but that's the equation before was simplified because we don't take into account the duration of the wake up for the idle state. So here, and we don't take into account also the static leakage, and we don't take into account the power on the slot this specific idle state. So it's a bit simplified, but we have more or less the information we need to compute this value. The static leakage is almost impossible to get from stock vendors because they don't share this information. So we have to assume it's zero. And then from there, we can do all the computation we need in our code. So the implementation today, we are relying on SMPU threads. So why we are using that is because we have a framework already in place for threads where the hot plugin thing is taken into account. So we have very small ops for this thread for the idle injection. These threads are in charge of idling the CPU. It's designed with lockless. There is no lock. It uses the play idle function, and it relies on CPU cooling, DT bindings. So there is no. It's compatible with the CPU cooling device binding we have today in the DT. Yes.
Looks like almost like power plant.
Yeah. The code is very
The power plant is the idle injection unit. Yeah, it is idle injection.
Yeah.
So the only difference is that power plant actually doesn't have the thermal part. I mean, you can use it for like power plant too, right? Which is the name. So it looks like you could use the power plant.
No, the power plant is increasing the idle duration. This is increasing the idle period.
Decreasing the period.
Decreasing the period. I agree. There are some common things. Okay? The idle injection routines are very common, but it's if you look at the code between the Intel power plant and the code in this driver, you see that it's very different. However, we can create a framework for idle injection threads that is common.
Yeah, idle injection threads. That's what I meant, because today power plant is basically just idle.
Yeah, based on workflows.
No.
That has its own thread.
This has its own threads. Actually, they are like idle task type. I mean, idle.
They're very FIFO.
Yeah, FIFO, yeah. But with in the idle schedule, idle step class.
But they used to play idle things.
Yeah.
I have a dumb question. In the previous presentation, talking about worst case wake up vacancy. So there are many reasons why some people claim that the worst case wake up script or idle state. So if you're in a situation where the idle state is completely restricted, then using injected idle as a way of doing power capping might not actually be as good as improvements. So is that something that let's take into account?
Definitely makes sense to use this to go with the frequency.
Well, I don't know how you've answered the two.
Was that to turn off the
Idle
condition voice?
I'm just asking how you balance the fact that sometimes, because you're using devices, idle injection might not be as effective.
The idea is to give them a lot of options, and then choose the right one.
Right.
Just to experiment and choose the right idle duration. Choose if the cpufreq cooling device is better than doing idle injection. If they want,
Yeah,
if it wants
But it's not
You might be able to
it might-
dynamically figure it out.
It might depend on the workload, because if there is some real-time workload, for example, you're streaming audio and you need to limit the exit latency and thereby limit the available idle states, idle injection might not be effective anymore.
That's also why have been decided to have a fixed idle injection, because you know how many time you will delay on the task to be processed.
No, you don't, because if you use play idle, you're just running as a Python thread and all the real-time stuff got preempted.
Okay. Yeah, I agree.
So the actual idle exit latency is still very relevant.
That would be the next step. Choose the idle state.
After that, well, it's the first step, idle injecting, and then we will provide more feature.
But yeah, so I'm still not quite sure why you chose a fixed period, no, a fixed duration, and then play around with period versus having a fixed period and playing around with the duration.
What's the benefit of that?
For example, if you take on a mobile phone, you have 16 milliseconds between each frame rendering. Let's say that in average, you know that you are using 50% of the time, which means that injecting for 4 milliseconds can be acceptable, but no more than that.
But if your period shrinks such
Yeah.
that there is two such windows,
I agree, but in this case, I
That's
mean,
true.
if you reach this situation, you're wrong whatever you are doing. But it's just that for that time, when you start mitigate, it's still acceptable for a responsiveness function.
So that's a kind of chart basis showing that the idle tasks are aligned. They are aligned perfect. You don't care about aligning all the tasks the same time. So we can by this way we can mitigate, decide to mitigate just big cluster, for example, not small cluster, just a big cluster. So we can split in two, so we have one cluster without the injection thread, and we have another cluster with by the injection thread.
Does the fact that you are going idling or actually imposing idle affect the governor predictions? And
No,
how do they interact at all?
I'm not sure I got
I mean, the fact that you're actually causing idle, the CPU to go idle, does this fact?
does it change the governor?
Yeah, how does?
No, it uses a function.
No, yeah, I understand that. But my question is that is the governor aware that it's kind of imposed idle instead of
No,
idle? Okay,
no, there is
a bypass.
right.
Results relevant for those situations. How about these on performance?
Well,
Because I guess, well, you're not only seeing cycles, you go down to file down, you're also flushing the cache every time.
Yeah.
How that is controlled.
Yes. So we have done that before, and we have now the implementation, and now we are experimenting that on the IK 6220. So the IK 6220 is a board. It's not big data. It's a board with 8 cores, 2 cluster 8 cores, 1 clock line. So the idea is just put it fuzzy, full load the 8 cores. Because it's on demand, we are in OPP max. So from the DT, we have different information. For the OPP max, we have the voltage, potency, dynamic, power consumption. So that's the equation giving the power consumed. We have the mitigated temperature is 70 degrees. So when we are reaching this, arriving at this temperature, we will begin mitigating to stay at this temperature, and that is supposed to be the power sustainable at this temperature. So if we compute, we use this equation with all the information we have in the DT. For one core, we have 660 milliwatts. For the 8 cores, we have 5,280 milliwatts. And we decide, that's our decision, to inject 10 milliseconds of idle time. So with the formula we had, that means in order to reach this power, enable power, we have to inject. So here we remove 1.5 is the wake-up latency for this idle state. That's the idle duration. That's the maximum power, the targeted power. And then that's the time should be the period of that's the period we compute. And that's the measurement. And the measurement we see here, we have the temperature increasing until 75 degrees, and it tries to stay at this temperature. Okay. And the green is the period. So at the beginning, we don't have any period, and then the period will decrease. So we are injecting more and more and more and more cycles. And then we are reaching here more or less around 40 milliseconds. So it's what we measure and what we computed is more or less the same. So for the thermal driver, the cooling device, we use a simplified approach because instead of having 1, 2, 3, 4 steps for the cooling device for the states, we just do that in percentage way. So we have between 0 and 100 steps for the cooling device. So if we ask, for example, 50%, 50% means we want to use 50% of the power we are using. So in this case, we are 75% of maximum power of the both cluster we computed right before. It's this value, 3,960 milliwatts, and that means we are using 75% for each cluster in this sock. And because of that, we can compute with a proportional factor the duration. We can compute we have a ratio between the maximum power and the power of requested power, and then from there we can compute automatically the running time of the equation. Again, up here. So these are the measurements with dry stone on 2 boards. So we have this board, IQ 6220 and IQ 3660. This one is much more faster, and it has some thermal constraints. The thermal constraints are very are stronger than the first one. And what we see is for idle injection, we have more or less the same. So for long times, that was your question, we use 2 seconds for idle injection compared to cpufreq. Because that's expected. I mean, that's something it's expected. We are adding idle duration, of course, it is longer time. So the idle injection is interesting to mitigate temperature, to drop the static leakage, but the drawback is it adds latency to the system. So we should be considered this as an alternative for cpufreq if cpufreq is not available. Or we can also use that as a secondary cooling device. So let's imagine the first cooling device is acting at 1 temperature, and then when we reach another result, highest result, we can switch to this one because that means the first one is not succeeding to cool down for whatever reason the hardware. So we go with something we accept drop performances, but save the hardware. So we are able to change the frequency, and we are able to inject idle cycles. Can we do something better than both of them? So here is the thermal behavior of the two stock we use as a reference, the two IT boards. So the green line is the IT big little. So that's the increasing of the temperature. And that's how it mitigates. We see that we have a lot of transition. And the other one is the IT 6220. And we see the temperature is increasing slowly, and then we have transition to mitigate the temperature around the 75 degree. These are the temperature specified.
Which government is
In this case, it's stepwise for this. For this.
For both of them?
Yeah.
Is that generally the best government?
Stepwise?
IPA
IPA is the
Fine, that we cannot IPA also. You can mislead it if you just So IPA is better, but you have to.
You have with the IPA, you have more or less the same. More or less the
Same effect.
Same effect.
If it's spiked.
So that's a reminder about the temperature around 75 and the changing the frequency. And here we see the change of the OPPs. So we have a performance loss. So we, for example, we have the changing OPP from 1.2 gigahertz to 960 megahertz. So we are dropping power from 5,218 milliwatts to 3,328 milliwatts. So what about if we don't need to go there, but we can have higher power? Can we do that today? With the cpufreq device. We cannot do that. We cannot achieve that. But if we add ideal injection at this point, we can, before changing the OPP, we can be injecting idle cycles. We have the same power. And because we are at a higher OPP, we are faster. So from there, if we are able to inject idle cycles and we are able to change the OPP, we are able to fill the gap between two OPP and have better performances by injecting idle cycles before switching to the below OPP.
Yeah, and I think they're far more consistent, and I showed in a table earlier as well, where you had the. Can you go back a few slides? Where you had the table. The standard deviation of the temperature with the injection is much lower than cpufreq.
Yeah.
And
That's again because you're using the wrong governor.
Yeah, the governor plays
Okay.
plays a role.
Because just modulating means if you do have two OPPs and then you want to be in between, if you just modulate your frequency so you alternate between the two
On our
OPPs,
window, the
you
average
should get a better result.
Well, from a power perspective, it will be the same.
Yeah, but you would get better throughput because you will actually be running some part of the lower OPP, but the voltage is low, so you heat up less. So if you integrate over everything, you should get more throughput by just modulating how you use the OPPs instead of injecting idle where you force the whole system to stop. But when you're running, you always pay the full price in energy for what you're doing. While if you modulate the two, then the time you spend at the lower OPP, you actually pay less for the work.
Yeah.
So when we should change the OPP, when we are inserting idle cycles at the higher OPP, we change the OPP when we have capacity equivalence. So when we have, for example, the capacity of OPP and we are injecting a number of idle cycles, and we are reaching the same capacity than the OPP below, then we change the OPP.
switch between the two of these, which I think is what I did with
Yeah, we
the
did
extreme
experiments with
correctly.
that, and it was better to oscillate between two OPP. The idle injection only makes sense at the lowest OPP to be able to get
At the
OPPs
lowest
below
OPP,
the lowest OPP.
At the lowest of the you're not sustaining your power slash level cap.
Yeah.
Then do I?
Yeah, yeah,
But if at the lowest of the you could, which actually. We have seen one or two examples of that.
Well, you're charging the battery and it's just doing some general thermal disarray.
That'll work. I'm not going to, but yeah. It's, yeah, then.
So that's the equation compute capacity between the capacity and this one OPP inside the factors and the OPP low with a ratio to internal between the capacity equivalence, so we can compare with the capacity of the lower OPP. So that's the result by using both. We see that here we are oscillating with around 75, and here we are having a mitigation which is constant until we reach a point where we have to the temperature is increasing a bit, and then we change the we are at the limit between both of the P, we change the P. Here we have some changes, and then again stable, then finish with a bit faster. We have 3 or 4 seconds extension before small gain of performance. That's in this case, for this test case and this board, it's more stable, and we save a bit of power, and we have a bit better performance.
So you're saying that with roughly 2 IPA, you can feel a little better.
Yeah.
We don't have these changes?
No.
That's the result of step one.
Sorry?
That's the result of step one. But wait,
This
is
one.
No, the one
no,
above.
the oscillation that you have over there.
Yeah.
That's exactly.
Doing something to mitigate for proactive, that's your budget. Sustain below that.
Okay.
Yeah, I mean, the overshooting behavior that you're seeing when you're stepwise.
It's stepwise.
And maybe you could just repeat with,
With IPA.
if you have, if the IPA does have to be tuned. If you tune IPA very aggressively with its proportional, then it actually
You overshoot
like that.
Yeah.
But if you correctly just see it completely smooth.
Temperature.
Is it easier when you say you have like you have
We have a tuned guide. When I first tuned IPA, it was when IPA was first created, and this is the actual version, and tuned that to bring up with. So I can't really tell you how you might get a better idea of the other stuff.
but this
It's
needs
not.
extremely more.
Yeah.
Yeah.
There was a reference from someone in audience going down to one multiple experiment to establish what's the good holding time to have that in the decision and what's the good value for sustained power. So there should be a 32 versus 4.
Okay.
Yeah, to me, tuning IPA is kind of it's hard task, but that's goes as well.
It's the time.
So
kind of opening a sidetrack in general with many different frameworks also in the schedule or actually but seems that sometimes we are missing this in-care space that allows to support the user in tuning, fine-tuning of these mechanisms. But it's a long story. We should probably just try to push it a bit more.
I mean, but that's not on power or scheduling. Any framework.
Yes,
like the framework
absolutely. Yeah,
kind of
that's
use
what
the
I
same
mean. I say it's really a general things that it's not easy, and maybe you come up with a solution because you don't see the fast way to tune something which is already there the proper way.
And because the system doesn't rely on API.
Yeah.
Implementing. And here's and maybe this is your
Yeah.
So, as a conclusion, I think we can have with using combo cooling device, even for some testing. I think we can have more options, and I think we can have better performances than what we have today.
Especially because we deal with the static leakage, which can be something like 30% of your power consumption.
Yeah, no,
Very
on some SSCs, and
So
with
that's fine.
the temperature it comes up.
The goal is just to remove these, that can be a significant part. And,
Yeah, I mean, a couple of comments over there, at least with the current status, right? First of all, as I mentioned over the menu list, there's a big question mark between this board and Intel Power Plant, right? Because there is an existing, I know that's specific to Intel, but it's never good to have two different drivers for the same conceptual proposal. So it would be good to look at the overlap of both. And I understand that they have chosen to implement in a different way, but still, these two proposals, they are targeting the same, even the same concept of injecting idle cycles.
Yeah.
So that there's a question mark over there. I would suggest to look at how both can be leveraged together.
I already looked at that, and it's pretty different for system. The first, well, the anti-core clamp is based on the MSR register.
Yeah, I mean, as I said,
that's the part. So we are on the DT. We are using variable idle duration. We are using fixed idle duration.
Yeah, so we're still working on that info thing since still June, already?
so the takeoff,
yes.
in, originally, but then started to work on time waiting.
No, I mean, just to comment,
So you would have to ask them if changing to fixed interval
or even given an option to change it.
Yeah, so it might, it might work for us as well to just vary the period and keep the injection work on.
Yeah, but
I don't know.
similar.
Yeah, just to make you, just to add another information. A couple of years ago, there was this guy from Samsung who sent a patch to actually use Intel Power Plant on our systems. So it is doable. I mean, there was a couple of comments that I had in the patch, but he never came back. But yeah, I mean, it's not that I cannot use the Intel Power Plant approach on other systems. You just need to, make it a little bit more flexible. And then, of course, remove the parts that are specific to MSRs and everything.
But just split.
Yeah, split it and make it like a generic layer where you can have like this injection part and the Intel or ARM approach or DT approach.
What I can do is I can split the idle injection thing, create an idle injection framework in the thermal framework.
Not in the thermal. So the idle injection is power clamping. It's a power clamping concept rather than just thermal. Because you can also power budget. I mean, you control the power budget. But if you
are say, if you want to stay within a given power budget, you can do that by agent.
Say you've overcommitted to the power rail of your rack.
Yeah, like that. Yeah, you can also do that by injecting idle. So it is a broader concept, not a thermal concept.
So
Yeah.
what should be the place?
We have a power clamping subsystem, power capping.
Then we should go to the power
Yeah,
company
and
system.
it can be used by the thermal. If somebody wants to use it for just power capping. We have, so there is the Raffle driver in the power capping subsystem now, but we could also have the power clamping there. I'm sure if it's not there, they don't remember that.
I think that was our primary.
No, yeah, that was the idea, basically, but I'm not sure that happened, so
I cleaned it up.
It was a couple of years ago, and then but we still need to fix the ACPI processor aggregator. Yeah, which does the same thing, by the way, but
can we
it's built by
delete
ACPI, so, yeah.
Can we get rid of that thing?
So it would be good
piece
to,
of crap.
it would be good to consolidate all the power, the idle injecting one, and then, But SPI has an idea of processor aggregator device.
Yeah.
PAD.
Yeah,
And then you implement that by
Randomly taking CPUs offline. It's an absolute horrible thing. Can we just please delete it?
so we can't delete it, but we can make it use the idle injection.
Right. That will be more special.
Yeah.
Okay, so I can create a framework to do the idle injection. I can do that, and then plug the cpuidle, the thermal in there, and
And the
if
power
Intel power plant wants to migrate to that.
Well, it's not a matter of what, or that's the one you just can change it to use split the power plant, move the idle injection part into the power capping subsystem, and then make the driver use that.
Sorry.
And make the power plant use the new kernel. That's it, because it should work the same way as it does today. You don't have to ask anyone. Just try to make it user generic.
Okay.
Yeah, and the other comment that I had was I was already said to compare against IPA would be also, have more fair number.
But if you, so my comment to that would be, IPA needs to be tuned, right?
But this
So does this.
Yeah, so my question would be like, is which here?
What do you think?
Why not? Can we clarify that? Because I don't,
How
I'm not sure it has to be tuned.
the same level, but I'm
What's
just
the
saying that
tuning
this one
that
also
needs
needs
to
to
be
be
done
tuned.
The tuning.
It's just to select the period.
Yeah, it's a selected period, but could be also the idle state. Decide to go and things.
But with the plate idle thing, I think always get the deepest available
Yes,
idle
yeah.
state. So that have to be a different thing.
It could be also play idle and use the idle state you want to go.
Yeah, well, that's, so there is one little problem with this. So on some systems, you have to disable certain idle states because basically they don't work. And you have to be, force them in any way because, some systems users want to disable like CC. It's not reliable. And you know, there's, so and we need to respect those settings.
But I think we still use CPU idle to select the idle state. It's just that we ask for the deepest available.
For the deepest available, but you can disable states through CSFS, and then you want to.
Right. So if you disable the C6, C4, and all
Yeah,
that.
that's what I'm saying. But if you would like to have and a way to enforce a city practice state, which is not going to work because of this problem, right? Because we will need to have a settings to say, but by the way, this is really disabled, right?
So what instead we can do is maybe shortcut the predictor, the menu governor, by feeding it a expected idle duration. They were going to inject this many nanoseconds of idle.
So we don't have to do that to the menu governor. You can just feed the function that makes the selection of the idle state.
So bypass the whole predictor crap.
Yeah, right.
Running out of time.
Okay.
Actually, just one other on this discussion. Some of the point I was making earlier, where the tunability of things depends on what other states you're allowed to use within the
Right.
and that makes tunability just a little bit harder. The effectiveness projection could be.
Also choosing the idle period. I mean, how easy is that? You need to know your entire software stack to figure out what you actually tolerate.
Yes.
That's not easy.
But you know, I think in courses where we probably was to make up. So kind of know what you really do. Depending on how that is set. But another protection of X intersections, they really detailed.
Yeah.
So,
This can be easy to figure out.
you can't just pick a period, basically.
In fact, you actually need a way to monitor this, the effectiveness of what you have selected, because that means it doesn't work for various reasons. And then you should be able to evaluate it. Yeah, well, okay, this doesn't work, we're just doing something else.
Yeah. It calls for a PID on the same.
Yeah.
Yeah.
Okay, so next step is go further on experimentation. See if we can have better results very significantly with IP. If that's the next step, with that, and have numbers. Thank you.
Yep.